Hello students, today we will discuss about intrinsic carrier concentration. We have seen that there are two types of semiconductors, intrinsic and extrinsic. Intrinsic are the pure form of semiconductors and extrinsic are doped semiconductors. As we have already discussed, in case of an intrinsic semiconductor, the carriers are due to electron-hole pair generation. When the energy gained by these electrons are more than the forbidden energy gap, then they will move to the conduction band. So, this electron, after getting the required amount of energy, it will move from valence band to conduction band. Similarly, those electrons which are getting energies more than the forbidden energy gap, they will move from the valence band to conduction band. Once the electrons move from the valence band to conduction band, they leave behind some empty spaces within the valence band, and these empty spaces are known as holes. You can see here the number of electrons that move to the conduction band is same as the numbers of holes created within the valence band. So, in an intrinsic semiconductors, the number of electrons generated in the conduction band is equals to number of holes generated in the valence band. This number is known as intrinsic carrier concentration. Now, if N is equals to the number of electrons generated in the conduction band and P is equals to the number of holes created within the valence band, then N should be equals to P, and let that constant number is taken as Ni, and this Ni is known as intrinsic carrier concentration. Now, we will find out what is the expression for this intrinsic carrier concentration Ni. In some of our previous lectures, we have derived the expressions for hole concentration in the valence band and electron concentration within the conduction band. Let us just see what were those expressions. The electron concentration in conduction band is equals to N, and that is given as Nc exponential Ef minus Ec by Kt, where Nc is a constant, Ef is our Fermi energy, Ec is the bottom of the conduction band. Here you can see this value is equals to Ec, K is Boltzmann constant, T is temperature in absolute scale. Also, we have derived the hole concentration in valence band. P is equals to Nb exponential Ev minus Ef by Kt. Here further this Nb is a constant, Ev is the top of the valence band. Here this is the value of Ev. Ef is again the Fermi energy, K is Boltzmann constant, and T is temperature in absolute scale. In the previous slide, we have seen that in case of an intrinsic semiconductors, the number of electrons is equals to number of holes, and that is known as intrinsic carrier concentration and represented by a letter Ni. From this, I can write Ni square is equals to Ni into Ni, and in place of one Ni, I can write N, and the second Ni can be replaced by P. Then we will get Ni square is equals to Np. Now we will substitute the values of this N and P over here, and we will see how the value of Ni can be obtained. Substituting this back into this equation, we can write Ni square is equals to Nc Nv exponential Ef minus Ec by Kt into exponential Ev minus Ef by Kt. This Nc come from here, Nv came from here, this exponential Ef minus Ec by Kt, it come from this expression, and this last term came from this expression. So, finally, we got Ni square is equals to Nc Nv exponential Ef minus Ec by Kt into exponential Ev minus Ef by Kt. Further, you can see these two exponential terms within this bracket they are multiplied with each other and hence can be combined to form a single exponential term, because we know exponential e into exponential b is equals to exponential a plus b. Using that relation, I can write ni square is equals to nc nb exponential. I will add these two terms, that is ef minus ec by kt plus eb minus ef by kt. Taking kt LCM, I will get ef minus ec plus eb minus ef. Here again this ef and this ef will get cancelled. Now ni square is equals to nc nv exponential. In the numerator, if I will take negative side common, then I will be getting ec minus ev. So it is exponential minus ec minus ev by kt. What is this ec minus ev? Ec is the bottom of the conduction band, ev is the top of the valence band, and the gap between these two energy states is equals to Eg, that is the forbidden energy. Thus, we can replace this Ec minus Ev by Eg. Replacing this Ec minus Ev with Eg, Ni can be written as Nc Nb exponential minus Eg by Kt. This is the expression we obtained in the previous slide. Now, let us do some simplification to this expression. In our previous lectures, what we have seen that Nc is equals to 2 into 2 pi m star kt by h square whole to the power 3 by 2, where this m e star is the effective mass of electron, k is Boltzmann constant, T is absolute temperature, h is Planck's constant. Also, we have found that Nb is equals to 2 into 2 pi mh star kt by h square whole to the power 3 by 2. Here this mh star is the effective mass of hole, k is again Boltzmann constant, T is absolute temperature and h is Planck's constant. Now we will substitute these two into this equation. So substituting this back into this equation, this can be written as Ni square is equals to, this is the value of Nc, this is for Nb, and exponential minus Eg by Kt, it remains as it is. Here in these two brackets, you can see this Me star and Mh star, these are the two terms which are differing, all rest are same. Here also 2 pi, here also 2 pi, kt, here also kt, h square is h square. So these two brackets, the difference lies only within this Me star and Mh star. If I will remove this Me star and Mh star from these two brackets, then I will be getting 2 pi kt by h square whole to the power 3 by 2 multiplied twice, that can be written as 2 pi kt by h square whole to the power 3 by 2 whole to the power 2, because this is multiplied twice. So Ni square is equals to this 2 and this 2, that became 4, and this term is coming twice. So it is 2 pi kt by h square whole to the power 3 by 2, and as it is multiplied twice, I can take the square, then this 2 and that square will get cancelled, and we will be getting the final term as 2 pi kt by h square whole cube. This M star whole to the power 3 by 2, Mh star whole to the power 3 by 2, as their powers are same, I can write them as M star Mh star whole to the power 3 by 2, and this exponential minus Eg by kt. This is the expression for Ni square. Then what will be Ni? I have to take the square root. So after taking the square root, I can get the final expression for Ni. So this can also be written as Ni is equals to, this square root of 4 is equals to 2. This 2 pi kt by h square whole to the power 3, that square root will give me 2 pi kt by h square whole to the power 3 by 2. Again here this m star mh star whole to the power 3 by 2 with this square root can be written as m star mh star whole to the power 3 by 4, and this exponential minus Eg by kt with this square root that can be written as exponential minus Eg by 2 kt. So, this is the final expression for our intrinsic carrier concentration, and that is also same as the electron concentration and hole concentration. In this expression within this blue box, you can see that this 2 pi k h square m star mh star all are constant, and what is the variable here? Only this t which is a variable. Rest all other quantities present within this box are constant. So, I can combine all constant terms within a single bracket, and I can take this variable t outside, or I can write it separately. So, separating the constants and variable, the expression for intrinsic carrier concentration can be modified as this 2 into 2 pi k by h square, because I am taking this t separately. So, it is only 2 pi k by h square whole to the power 3 by 2 m star mh star whole to the power 3 by 4, and this t and power is 3 by 2 that I have taken separately. So, it is t to the power 3 by 2 exponential minus Eg by 2 kt. Here all the quantities within this bracket are constants. So, I can replace this bracket with a single constant, that is equals to C. So, this total thing is replaced by a single constant C, and this t to the power 3 by 2 exponential minus Eg by 2 kt. This shows that the intrinsic carrier concentration depends on the temperature. As the temperature changes, there will be change in carrier concentration. That is obvious, because as the temperature changes, the electrons present within the valence band, their energy changes, and the number of electrons moving from valence band to conduction band changes. As the number of electrons are changing, number of holes will also change accordingly, and we will be getting a different value for intrinsic carrier concentration, that is Ni. Finally, let us see what are the quantities on which this intrinsic carrier concentration depends on. First one is, it depends on the temperature, that we have already discussed. Here you can see there is a temperature dependency coming from this term and also from this. So, the intrinsic carrier concentration depends on temperature. Coming to the second point, it is independent of Fermi energy and position of Fermi level. You can see here nowhere we are getting the Fermi energy EF. So, it is independent of Fermi energy and position of Fermi level. The intrinsic carrier concentration varies exponentially with forbidden energy gap. This EZ is the forbidden energy gap. So, it varies exponentially with forbidden energy gap. Further, it depends on the material of the semiconductor, because the forbidden energy gap is different for different semiconductor materials. Like for germanium it is around 0.6 electron volt, and for silicon it is around 1.1 electron volt. So, depending on the value of Eg, we are getting different value for intrinsic carrier concentration, and this Eg changes from materials to materials, and hence the intrinsic carrier concentration depends on the material of the semiconductor. Today we will stop here. Next class we will continue our discussion with Fermi level. Thank you all. Please subscribe to my channel, because all the materials which I am posting are in a sequence. So, whenever I am posting a new video, the notification will come to you and you can see the video immediately. Further, if you are finding the contents of this video are useful, please press the like button and share the link with your friends so that they will also get the benefit. Thank you all.